Muñoz-Reja and Távara at the University of Sevilla. Today I am going to present my recent work related to the moving prediction of using coupled criterion of finite factor mechanics based on the new formulation PMDC. And this talk talks about a new strategy in predicting the crack onset as well as the crack growth in a homogeneous material using the linear FEM solutions. And my talk is particularly relevant to those of you who are doing the numerical simulations in the presence of crack and also to prediction of crack onset in using the FEM solutions. So we organize this talk in the following way. So at first I will begin by giving you an overview, a quick overview of coupled criterion and also the PMDC criterion. In the second session I will focus on the methodology that I have used by explaining the numerical procedures as well as some of the coding steps. So in the third section we will consider some of the first results obtained during the coding test using the classical fracture examples. In the final section I will conclude my talk by mentioning the key advantages of this strategy as well as the future scope of this code. So moving on to the first session of the talk is that is the state of the art. So before talking about the new formulation, the PMDC, I would like to say a few words about the coupled criterion proposed by in 2002. So in the framework of finite factor mechanics, the coupled criterion postulates that the simultaneous fulfillment of both energy and stress criterion are necessary in the crack prediction. And this hypothesis contains two types of criteria which commonly used separate way in brittle and constitutive materials. And as we know that the stress criterion is commonly used to predict the failure in the absence of stress singularities, whereas the energy criterion is employed in the presence of cracks. So he discussed the condition of fulfilling both conditions by presenting evidences to corresponding classical fracture problems in different materials. From then on, a great amount of work has been published or presented by applying this criteria in very diverse problems of crack initiation in different materials. Additionally, it is fair to highlight two relevant contributions by Professor Peter Cornetti in 2006 and also Taylor in 2005, which are the key for the subsequent evolution of this coupled criteria. So, an alternative formulation was proposed by Professor Mantič in 2014, assuming the quasi-static loading and neglecting inertial forces. So, following the formulation, the coupled criterion can be defined as the minimizing the summation of pi plus r, where pi is the potential energy of the state and r is the energy dissipated with the new interface crack surface. The key idea behind this formulation is that a new crack surface can only appear on those regions where sufficiently large stresses are applied before the fracture process occurs. Therefore, the stress criterion would work as a filtering process for the energy criterion because in some cases, this criterion without considering this stress condition would inaccurately predict crack initiation for too low applied loads. So I am moving on to the methodology. The finite element method is widely used to solve the problems in the field of fracture mechanics. In the last 2 decades, there are several numerical techniques have been developed to improve the accuracy of the solutions in 2D linear elastic fracture mechanics. For example, extended finite element method, floating norm method, and also the phantom norm method. The major challenges that we face during the numerical implementation are as follows. The first one is the complexity of the new numerical methods, such as especially the extended finite element method, because we need additional degrees of freedom and also the problems occurs due to the transitional elements. And also we have some problems with the when we implement the element deletion method and also the elements complex splitting algorithms. So finally we developed a method, numerical procedure without any kind of a complex splitting algorithm or even element deletion method. And we model numerical procedures in the 3 independent modules for the simplicity of the code testing as well as its functionality. So the first module is called stress criterion module, which is implemented in conventional finite elements in Abacus. And the second module is called U-Inter. It's an interaction subroutine used in Abacus. And the third one is the energy criterion module, which consists of some linear FEM solutions. So So I am moving on to this first model, that is the stress criterion. As I mentioned, it is implemented in the conventional finite elements in calculus, and this stress criterion is developed. Stress criterion is developed in using major three steps. The first step is about the code extracts the node with the maximum principal stress. Then in the second step, the code will generate the approximate fracture zone or the cracking zone by creating a polar coordinate system on that node with the maximum principal stress and looks for sigma theta. In the final step, the code limits that fracture zone or the cracking zone by applying the stress limit, that is sigma c, and using the largest distance rule, the code calculates the possible crack path from the stress criterion. So this is the second module. So in order to apply the energy criterion on the crack produced from the stress criterion, the surfaces of two surfaces of the crack was modeled using virtual springs, using the abacus interaction subroutine called U-inter, and the interface was modeled by a continuous distribution of springs with a linear elastic behavior called a linear elastic brittle interface model, also called Levy. So the image shows how the springs behave during a normal loading and also the shear loading, and the normal and shear stress at that point is proportional to the normal and tangential relative displacement at the specific point. So this is the formulation for the Levy, and here the KNN and the KT are the stiffness or normal and tangential stiffness of the spring for an undamaged spring, and the interface failure criteria can be defined in terms of the energy release rate and also interface critical energy. So the energy release rate means that it is defined as the energy stored by the springs for the stress, shear stress and also the normal stress. And the critical interface energy can be expressed in mode 1, also in mode 2, according to the fraction model mode mixity characterized by the mixity angle here. So from this relation, if G or the fractionality of the spring is higher than the GC or limit, then the code will break the spring. If it is vice versa, the code will heal the spring. So like that, the code can create a crack as well as remove the crack by just damaging the springs or healing the springs. So moving on to the third model, that is the energy criterion. So inside the energy criterion, we have several case models. So I am going to explain the algorithm with one case model. So for example, consider all the springs are active, and the code will run some linear simulations and obtain the fracture energies of the spring, and it compares with the GC value, as I mentioned in the previous slide. And here, accordingly, the code will damage some springs, and the code reruns the model with the new model, updated model, and again it calculates the fracture energy and compares with the GC value. So at the end of the J step, the code will save the final pi plus R value of the final model, and that value will be compared with the other several models. So in this slide, we have two major information. The first one is about the end cases. As I mentioned that there are several models inside the energy criterion. It means that there are several starting case. For example, I started the initial model for the energy condition is fully activated spring. Then it goes through the energy criterion and we obtain pi plus R values. So similarly, we start with another case model with the fully damaged spring and we obtain another pi plus R value. Then finally, the code will compare all these pi plus R values and obtain the final crack length from the energy criterion. So I would like to mention the DCCT method here because I use it for the calculating the potential energy of the system because it is very accurate. It produces accurate results, and it is based on the idea that the change in potential energy, elastic energy due to the certain crack growth is identical to the work necessary to close the crack to an extent equivalent extension. So I am just fast forwarding the results that I obtained from the code testing. The first classical fracture example is the central crack subject to tensile loading. So here we have four main plots, which is the horizontal green represents the UTS prediction, and the inclined orange one represents the linear elastic fraction mechanics prediction. And here we have two kinds of plots for the finite fraction mechanics. One is for point-wise criterion proposed by Professor Legion, and another one is the average criterion proposed by Karthik. And I will zoom in the results from the simulation. So our simulation coincides with the point-wise criterion because we are using the point-wise criterion for the stress criterion. So as the next step, we removed the crack and we introduced the circular hole, and we also checked with the analytical solution. And here we have two plots, one is the energy and the stress criterion, and we exactly matching with the analytical solution. And also we checked with the small radius circular hole, and again also we are getting the better results compared to the analytical solutions. And this is the result for the the previous was the biaxial loading, and the next solution is about the uniaxial tension, and this is the first result that I just obtained from the quadrant. So for the conclusion part, that is the last part. So as in the U-inter, we have successfully cascaded the interaction of the two surfaces of the crack without leaving any physical thickness there. And we are, as a future scope, we are considering development of a U-inter subroutine instead of U-inter subroutine for better results and comparison studies. And in the energy criterion, we didn't use any kind of element deletion method nor element splitting method for the simplicity of the core. And we are looking for advanced machine techniques to extract the fracture energy of the springs for the better results. And during the quarters, we matched with the analytical solutions in better way, and we are looking forward to do the same procedures for the multiple cracks and also for adhesive layers. So that's all for. Thank you for your attention.
Thanks, Karthik. Time for a few questions.
Thanks for the talk. I have a question of curiosity regarding the Lépine.
Okay.
Because you use this to calculate the incremental energy release rate. And what is the advantage of using this? It looks to me similar to a gaussian zone, instead of not only releasing the nodes along an interface. What is the motivation to use the Lépine?
Yes, because using the Lépine strategy, we can heal the springs. It means, like, for example, from the stress criterion, if I have a larger crack length, and from the energy criterion, if it is saying that it's not sufficient to break that amount of crack length, then we can also heal the springs using the Lépine, because we can keep active that spring in the next iteration also.
That is practical.
You need a damage field in the crack, and there is some damage variable, and this is useful. The damage variable is there are several crack competing. It can be very practical, very efficient. We could do it just with crack length, but then the optimization is not correct.
And it is from the linear solutions. We just run the linear field solutions.
We use the stagger scheme alternative minimization method that it's 10 limit this kind of parameter for damage, and this is very advantageous. We hope it will be very efficient.
Thank you.
Okay. Another question?
It seems to me that we did not comment on the values of the normal and tangential stiffnesses of the springs. How do you choose them?
Okay, so we conducted some of the stress experiments, and I didn't disclose here because we are about to publish the things. So it depends on the, lot of parameters are there to choose the stiffness of the springs. So we will publish it.
Secret.
Yes.
Some other questions?